We're very pleased today to have Brandis Whitfield of Temple University talking about short curves of n-periodic mapping tori.
Yeah, thank you so much for inviting me to be here. And this is kind of novel stuff, so I'm happy to slow down, make sure everyone understands, what's going on, what definitions are. So I just want to start off by saying, what are the kind of objects that I like to think about? What's the type of mathematics I like to think about? And so these three pieces here, first is the arc and curve complexes of surfaces. Usually I like to think of curve graphs and arc graphs and the geometry, kind of torques of them. The next is big mapping class groups of surfaces, so homeomorphisms of surfaces up to isotopy. And the next is the geometry of hyperbolic three manifolds, particularly fibered three manifolds. So I'll define some, I'll give you definitions of the things that you need here. But the math that I like is the math that combines all of these three things together. And these topics have been, the interplay between all of them has been studied when my fiber is a finite type. But what I really want to convince you of today is that these infinite type surfaces also have a really interesting story to say, and it's a good story to tell. So I just want to start off with telling you more about what's going on in the finite type world. So let's start with a closed surface. I'm going to call it F. So if I have a homeomorphism of that surface, let's call it phi. And I'll say it's orientation preserving. Then I can build its mapping torus. I'm going to denote it as n phi, kind of controversial. So I'm going to take that surface, cross it by the unit interval, and then, so let's do that. Small picture, maybe times. And then I'm going to glue the top to the bottom using that map phi. So x comma 1 is going to get glued to phi of x comma 0. So let's do that. So now that gives me a closed three manifold, and really celebrated theorem of Thurston is that this closed three manifold and phi admits a hyperbolic structure. It's symmetric. If and only if phi is isotopic to a pseudo-Anosov. The two. Homeomorphism. Okay, so some cartoon I like to draw is just like, this is the mapping torus. It's a closed three manifold, and there's really some topology happening here, but this is kind of a picture of it. So if you haven't seen this before, I'm only really concerned about fun facts about these pseudo-Anosovs. So maybe they'll recall, let's recall some facts. So the first is that phi admits no periodic curves. So by that, I mean, I don't have up to isotopy, I'm thinking. That I mean a curve, call it alpha, with periodic if under the math, phi to the n of alpha is alpha again. So that doesn't happen with pseudo-Anosov. So we should think that these maps are mixing up my surface very heavily. So they're mixing up the surface heavily. There are no periodic curves, so it doesn't preserve any multi-curve on my surface. But it does preserve a generalization of a multi-curve. It preserves a lamination on the surface. So phi preserves actually a pair of laminations. They're geodesic laminations, measure laminations. laminations, called the stable and unstable. Also the unstable and stable. Laminations of phi. And I usually denote them by lambda, little lambda plus and little lambda minus. So what do I mean by lamination? I mean, it's just some collection. It's some collection of disjoint geodesics that are really like homing around in my surface. So, you know, I can't draw an accurate picture because there's kind of locally infinite, but let's pretend, you know, these geodesics are like going on forever and forever, and they're kind of spinning around. Here, there's gonna be a local picture. And maybe this one. Maybe it's going like that, and then it doesn't really just sit somewhere else. So I'll call this lambda plus, and this is lambda minus.
I'm a dynamicist, so just so that I understand, you're basically, these are still what I'm used to from Anosov diffeos.
Exactly.
Just points that have the same asymptotic behavior as I do plus or minus.
Exactly.
The same thing.
Exactly. And I get these geodesic laminations just by pulling those leaf lines tight to geodesics. So now it's not these I should not think that these geodesic arcs are filling the whole surface.
But so why do you say geodesics?
So you can always pull them tight to be geodesics. Each line, each leaf here is a quasi-geodesic. If I lift it up to the universal cover, it's a quasi-geodesic. I can always pull that quasi-geodesic tight to a genuine geodesic of my surface. So now when I go back downstairs, it's genuine geodesics. So I'm throwing out all the ones that are parallel. I just want to look at the geodesics. Is that okay?
I think so.
Okay. Yeah.
Yeah.
So yeah, if you're used to the foliation definition, that's okay. The measures. Yeah. That's fine. I just don't want to think about all of those arcs. I just want to think about the geodesics. Is that cool? Okay, so I just have these geodesic arcs that are living on my surface, and I have some homeomorphism that preserves them again up to isotopy. I'm usually thinking of isotopy here. Okay, so that's kind of hard to think about. Like I usually want to think about these in terms of like an arc or curved graph of the surface. So maybe I'll define that. So let's put them together. So curved graph of S. So it's vertices. I guess I'll say F, but really of any surface S. I'll say any surface. So the vertices are isotopy classes of simple closed curves and proper arcs. And maybe I should be careful. I want like proper isotopy on a bigger surface, proper. Just be super careful. And then the edges are going to correspond to disjointness. So maybe you're more familiar with just the curve graph. I'm kind of throwing them all together. I'm going to call this AC of S into one graph. And it is quasi-isometric to the original curve graph, if you're more familiar with that. But I just like to see the arcs together.
What's an arc?
Oh, an arc is a proper embedding of the real line. So in this case, so for example, on a closed surface, there are no proper arcs. I want to make sure that it's actually properly embedded. So an arc should be mapping to a surface to its boundary. So I'm trying to be more general by saying I'm not just thinking of closed surfaces here. I'm okay with thinking of surfaces with boundary here. So let's just, yeah. So I have the boundary component here. Here's a simple arc. And then I have the green curve here. That's also an element of this argent curve. It's also a vertex. Is that okay? So You think of all the possible ones you can have up to isotopy, those are the vertices.
So, okay, if I don't think about the boundary, then I don't need to think about arcs.
Exactly.
Okay.
It's just the curve complex. Yes. But I want to think of things with boundary or things with ends. Like these infinite type things have ends. I can think of arcs that are running from this end to this end. Is that okay? Okay, so these are,
Can I ask you also just to situate myself, like I'm from a different field, so should I think of this as a small finite graph, or is this a very
Ooh.
infinite graph, or?
no, yeah, let's say some facts about it. So this is not only is it infinite, it's infinite. Like there are infinitely many vertices. It's infinite diameter. Maybe I should have said, ended with that one, it's more shocking. It's infinite valent. But it is delta hyperbolic, so this is why we like really care about it. So the geodesics, if I attach, I have these edges, I'm just using the path metric on this graph. I can attach any three vertices, it's connected, that's important. So I can connect two things that intersect. Actually, that's a path from the red arc to the blue arc. It's just red, green, blue. Yeah. So I can connect geodesics inside of this graph, and the delta neighborhood of 2 always covers the one edge. The one edge is always covered by the delta neighborhood of the other 2. There's a uniform delta that I can choose to make that happen. So you think that these triangles are uniformly thin. That's what we say. So it's a thin triangle condition. I'll say delta then. Okay, so geometric group theory, mapping class group people love this object.
What's the topology of this thing?
So I use complex here. So some people want to make sure it's like a flag complex, so they'll glue in, simplices whenever I have a complete click. But I'm not interested in that. I only really care about the coarse geometry. So I really genuinely just want it to be a graph. For my purposes, I don't care about it that it's a graph. But when people actually build the genuine curve complex where they make sure all the simplices are there, I believe that the boundary of that object is a n sphere. So there's not, I don't know. Yeah. Okay. So I really care about distances in this curve complex. If I have 2 vertices that are far apart in the curve complex, infinite diameter, I can always find vertices that are arbitrarily far apart. You should think that they're, mixing very heavily inside of the surface. It's not even just that they intersect a lot. It's that I can't even find a path from one to the other, like in that finite time. They're like very, very complicated on the surface. So I'll just vaguely write distance measures mixing. That's kind of a mnemonic you should think.
You don't mean mixing in the ergodic sense.
Oh, sorry, say again?
You don't mean mixing in the ergodic sense.
No, I mean, yeah, there's not really a rigorous way I mean it other than the distance is very far in the curve complex. Let's see. All right. This board is pretty full. What did I want to say here? I wanted to say, okay, so I have this graph. I would really like to measure these laminations inside of some curve graph. But each arc, each geodesic, red geodesic here, geodesic arc here, intersects each blue arc infinitely many times. So I can't really measure it inside of this arc and curve complex. So I need to do something more subtle. So, can I write on the backboard? Or no?
Yeah, you just will lose the.
Yeah.
I mean, it's up to you if you still want us to be able to see that one or not.
Yeah, maybe not. Maybe I'll let it peek out a little bit there. No, I won't. Excuse me. I didn't use the board. Okay, maybe I'll do it here.
There's room left on that board over there.
Yeah, that's true.
I feel like on these 2, you have a plan for them, so.
Yeah, I still put pieces to stay on that side though. Okay, so remember that I have those arcs that are really mixing. And they go off and they're going off forever. Can't draw them. The time I'm doing this. So these should be, they're intersecting infinitely often. But instead of looking at it on the closed surface, maybe I'll look at a subsurface. So I'll say that Y is an essential subsurface. So now, for example, we can take this annulus here. So now, like if I look at the cover corresponding to this annulus, probably the most rigorous way to do this. I mean, what do I see from these arcs? I just see that they're just winding around each other. How many times did I do this? I guess I did that. Sure. Yeah. So, and all the other arcs are kind of parallel to this one. They are parallel to this one. So to me, it's like, why would I think about every single one of them when I can just think of a couple of them? So I can define the subsurface projection. So I'm going to write the notation. So I'm measuring the distance between lambda plus and lambda minus. In really, I mean the arc and curve complex of Y. So every leaf of lambda plus is going to project to the curve complex of Y. Every leaf of lambda minus is also going to project to the curve complex of Y. It's connected, so I can measure their distance in that curve complex. This is that distance. Okay. Hopefully that's okay. Take that for granted. And I use an annulus here, but you know, any essential subsurface is fine. Okay, what's my plan? Let's go back to this word. Oops, I can't about the good. So now, given a subsurface, an essential subsurface, it's allowed to have boundary. I mean, it will have boundary. I have two pieces of information. One is this projection distance. Given this, okay, the subsurface, and you know it's mapping torus, and some homeomorphism is mapping torus. The first piece of information is the subsurface projection to the laminations.
Sorry, can you just, I didn't quite understand what this distance is.
Oh, yes. So, okay, let's just go back to the annulus here. In the annulus, it literally is how many times these arcs are intersecting in Y. But in general, I can take any subsurface. It could be, I don't know, I don't want to mess this picture up too much, but maybe instead of this yellow annulus, I'll take like this subsurface. And now they're kind of going off forever. Well, they're growing off, but they should be coming back. They're always coming back to here. Every single leaf of lambda plus projects to a proper arc. If I look at an arc and I'm intersecting it with a compact set, I see these little compact arcs that are intersecting it. So every single one of them is a proper arc of my subsurface Y. Is that okay?
The distance does depend on the Y.
Yeah, no, okay,
Yeah,
that's
okay.
fine by me, just the intersection number is something.
Okay.
Yeah.
Conceptual.
So it is, you should not be able to compute this. Maybe that's not helpful for you or not, you're not happy with it. But if I have a general subsurface, it's, you know, I have a homeomorphism, it's hard for me to compute that, but I know it is a number that exists. In the annular setting, it's just the intersection.
Your point before with the different parallel lines was that intersection number just doesn't depend on the line that I choose or something like this.
Exactly,
Okay.
yeah. These are distance one if I take the parallel. I might be off by 1 at most. And in coarse geometers, we don't care about uniformly bounded error. It's like, all right, whatever, 1, who cares? Okay, so I have this subsurface projection distance that's telling me something about the homeomorphism, because it's telling me about these laminations. And on the other hand, if I have some subsurface, let's just say this one, well, I know it's a subsurface of n phi I'm mapping towards. And this is kind of a misleading picture. This is not capturing the geometry of this mapping torus. Like if I want to pull these tight to a geodesic, they probably aren't living here. They're living somewhere else in the manifold. So I can pull the boundary tight to a geodesic and consider its length in the hyperbolic metric. So already, length of geodesic. Probably total length, some of them will, why not? Geodesic. Okay. So a theorem of Minsky puts these things together. So the theorem says that if this thing is very big, then this thing is very small. So a lot of mixing, if my subsurface sees a lot of mixing between these laminations, then the boundary of that subsurface is very small inside of the manifold. That's kind of how you should see it. Maybe I will quantify that carefully here. So let's just say,
So you're thinking of this suspension space that you have.
Exactly, yeah, this mapping torus suspension, yeah.
Mapping torus, yeah. So you're thinking of the boundary as sitting inside of it.
Like y, yes.
You're measuring the length of it, or what are you doing?
Right, I'm like up to isotopy. Every isotopy class of curves has a unique geodesic representative. So I'm pulling every single one of these components tight. Maybe it's over here. Maybe this is the geodesic representative. Or boundary y.
Saying that one is shorter.
Yeah, that will be short if this is big. So let me quantify it carefully for you. If that would be helpful. Okay, so let's, what year is this? 99, I'd say. Yeah. So let's fix the surface F, the fiber surface F. Then for every epsilon, I can find you a K, positive, so that, okay, so let's take any pseudo-Anosov. For any pseudo-Anosov, B of F. So that pseudo-Anosov gets these two laminations, lambda plus and lambda minus. And it gets its mapping towards n phi. Okay, that's just things I get for free. Well, thank you, Thurston, for giving me these things. So then the statement says, okay, this K is pressure. If my subsurface projection is bigger than K, then the length of the boundary of Y is less than epsilon. So this is the statement quantified very carefully, but you should just think big projection gives me short curves. This is exactly how I build short curves. And this is like an important tool that was used to prove the ending lamination conjecture. Like understanding where these short curves are is exactly what gives you like a model, a coarse model for these manifolds. So this is kind of why I was kind of interested in it. So, okay. So my work, I'm trying to extend this theorem to now the world of infinite type surfaces. They have homeomorphisms that are sort of like pseudo-Anosovs, and that theory has been developed over the past, I don't know, 10 years. It's pretty more less, maybe the past 5 years. It's pretty recent stuff. Okay, so we'll come back to the cycle here. Okay. So now that was the finite type world. So we're gonna now look at infinite type surfaces. So let S be an infinite type surface. I'm going to restrict it so that it only has finitely many ends. And I'm going to also restrict and say I only want non-planar ends. So people tend to say this is accumulated by genus, but whatever many ends you're thinking of, you can always build a surface. It's a unique surface that has, that many genus going off to all those ends. Here's the three-ended one. Here's the ladder surface that's two ends. I like the ladder. So. Okay, so now we can play the same game. We can look at a homeomorphism. And then I can build the mapping tools. So now I'm going to call it MF. And I'm going to, again, cross by 0, 1. And then I glue the top to the bottom using the map F. So here's a little cartoon of like the ladder surface. I don't know what. So for example, what's something that, I don't know. You can pick something that's compactly supported, let's say. To me is not interesting. Say the support of the homeomorphism is here. I don't really like that. Some people study that, it's fine. But what happens with this mapping torus? This part is just the identity map. So it's just, you're just gluing this infinite piece, which I know has not finally generated pi1, and it's just getting producted by a circle. So this piece, it's going to force the fundamental group of the mapping torus to not be finitely generated. So like, I don't really want to deal with that. I want a manifold that is tame. I want a manifold that I can compactify, I can hold in my hands. So I don't want to think of just like throwing finite type homeomorphisms into my big surface. I want something that's like distinct, something's different. So these end periodic homeomorphisms are like the things that I'm interested in studying. So let me define them for you. Homeomorphism F is end periodic if it's let me see. Because each end, I'll write it as that epsilon of S is either repelling or attracting under F. Okay, so let's just do example by picture and then we'll define it formally. So let's imagine I have like a translation where I'm translating each one of these two-hole tori, one by one. And I can kind of visually see, all right, this end is, the map is attracting into this end and repelling away from this end. But how do I write that rigorously with mathematics? So let's say, so what does that mean? What does it mean to attract? This is red for attract. It means I have a neighborhood of this end. I'm going to call it U epsilon plus. So there is a neighborhood. I use that epsilon of epsilon. Let's call it U epsilon plus. So that F of U epsilon plus is contained in itself, properly contained in itself. Let's do it. And if I keep doing it forever, I'm forming like a neighborhood basis of the end. So I'm approaching the end. Let's write that. Yeah, let's do that. So I take Fk of U epsilon, do that forever. Let's do just pause it. I can't really write off space. Okay, because it forms a neighborhood basis. But that's just a formal way of saying, you know, that those neighborhoods are approaching that end. Okay, so what's happening? I have rho, I look at U epsilon, I apply rho, and I live inside of myself. Live inside of my original. I apply rho again, I live inside of the original. I apply rho again. Like I should think that if I keep applying rho, I'm converging onto that end. So repelling is the exact same way. In fact, I could just say it's attracting under F inverse. I have this inverse, this negative neighborhood of this negative end. And if I apply them in F. Let's see. I have that F inverse U epsilon minus, this is going to be the U epsilon minus. Okay.
You know what they're called end periodic?
Yeah, so I tend to brush this under the rug, but I actually don't care how many times it takes me to get back to U epsilon minus. So I could have a surface like, let's do a doodle here. Sorry. I could be like shifting in this end, but then I click over here.
I see.
Yeah, so then it takes me 2 times. The period of my end is 2. So a lot of people they always think of pure mapping classes, but the general definition doesn't have to be pure. You could mix up the ends. And in the other sense, even if the map is pure, like this one, the point is that like this region here is now like a fundamental domain for the attracting end. I just see this genus 2 piece over and over and over again. So it's like, it's periodic in that sense as well. And that is what's really helpful to say, what I'm going to say next. So now I have this end periodic thing. Let's do this. Why is it so special? Well, it gives me a tiny mapping torus. So I'll say this fact, I don't know. This is due to Fenley. So if F is unperiodic, then its mapping torus is T. That means it's the interior of some compact free manifold, which I'm gonna lovingly call MF bar. This is for the compact free manifold. So just saying what the cartoon is. So maybe I'll just tell you what this one is. Okay. So example, for the handle shift, the mapping torus of rho, where rho is the handle shift, is just the genus 2 surface cross R. Cross R. And of course, that has a compactification. You just give me the top one and give me the bottom one. Sure, let's say negative infinity. Okay. So if you, I don't know, take time and try to understand why that's true, it's not surprising. It's surprising when I first saw this fact, I thought it was very surprising. But if you understand this handle shift, the rest is a generalization of that. But here's an idea of how, so this compactification happens through flow lines. So when I'm building the mapping torus, I have this suspension flow, which just tells me go up. It's x0. And now as I go up, I hit. As I'm going up, I'm applying the map. So now, what happens if I take one of these nice regions, these 2-hole tori regions, and I flow? Well, when I flow up to the one slice, all right, that's me being here, I keep flowing, And I keep hitting myself again. I just see the same picture over and over and over again. I hope that's okay to imagine while crowd this board. But now if I wanna just like end compactify by flow lines, I want each of those flow lines to have an endpoint. So every flow line has a representative that lives in this domain. And then what's the last thing I need to do? I need to realize, okay, well, all the flow lines on this curve are identified with flow lines on this curve. So if I take this two-hole torus and glue those two curves together, I exactly get this genus 2 surface, this closed genus 2 surface. So that's like how we get this picture. And in general, these n-periodic homeomorphisms are kind of shifting by some number of genus, kind of by this definition. So understanding the compactification for a general homeomorphism is just really this picture. Okay. So maybe I'll pause for a second. Oh, something behind her? I don't.
No, I'm just trying.
Yeah, it's a lot to take in.
Yeah.
So now we can see that we get tame compact 3 manifolds with boundary. What's the cartoon here?
Greg, can I ask you a question?
Yeah, for sure.
For on that top board, when you say compactified by sigma 2 cross closed interval, where does the
Oh, I guess I mean like this here is sigma 2 cross R. So then I can, what's a natural way to compactify that? Maybe to get a closed 3 manifold with boundary, well, I just include an affinity point at each point.
I see, so you're compactifying just the ends in, I thought you were gluing in an entire sigma 2 cross R. No, okay.
No,
You're just gluing in the ends.
it's sort of both. It's kind of the same thing.
Oh, okay, I see. Okay,
Yeah.
Either way.
Yeah, either way is good.
Gluing up the sigma.
Yeah. But I do want to have like a distinct end here, close these off, and a distinct end up there, which I can't reach. So maybe I'll draw like a general picture. So for example, there we are. Like if I had like a shift going here, a shift going here.
Wait, so this is like a universe, like, or not universe, but this is like a cover picture. So the 3 manifold, so is the 3 manifold gonna end up being the with like the quotient of the one, like of the torus cross R, or the several genus or whatever cross R.
Yeah, so
So like the compact surface cross R that you're getting there, is that
that will always be the end. That will always be the boundary component. But this is like the most basic picture that could happen where the manifold is a product. But in general, it should have more topology. So the silly picture that I usually draw, so for example, like this one, okay. This one will have 3. This is what the topology has to be if I have candle
so
shifts
in
going
this one,
here.
so if you're taking actually and you're gluing, then when I see, because that curve got mapped to that curve.
Exactly.
Those would actually get glued
Right,
when
in the
you do the
limit.
mapping torus.
Yes, but it's like
Okay.
it's this curve at level 1
Right,
identified with this curve at level 0.
right,
Right.
yeah.
So
Oh,
the flow lines are the exact same. So if I'm thinking of endpoints of flow lines, they limit to the same yellow curve at the boundary. Yeah. So something like this, it's boundary. All I know, I only have information about its boundary. I know its boundary is genus 3, and the union of genus 3 and genus 2, and 2 genus 2 surfaces. But I always try to make it clear that like this thing can't be a product. But in general, like they should have some topology going on here. And that topology should depend on whatever's happening kind of in the core of this map. So I've been drawing shifts But this definition is so general that it only depends on the ends. So I could compose one of these, for example, with like a pseudo-Anosov on here. So I'm gonna call this C, the core. Let's say call the handle shift row. So I can take a homeomorphism, which is like the composition. B, which is acting on C, this core, times rho. And now, I don't know if it's a pseudo-Anosov, it's also mixing up curves pretty heavily. So I shouldn't think that there's anything simple going on here. There should be complicated things happening.
So who's the role?
Rho, in this case, I'm thinking I have a strip of genus that I'm kind of embedding into my surface. Maybe I have another one here. And I'll call that composition rho. Thank you.
Yes.
Yeah. So is that cool? Yeah. Okay, so then I shift and do pseudo-Anosov, and that's also an n-periodic homeomorphism. It's mapping towards looks like this. Okay, so now I have a tame three manifold, but I like hyperbolic three manifolds. So I want to apply, these hammers of Thurston to try to understand, okay, well, when can I give this manifold a hyperbolic metric? And it should be exactly when my manifold has no tori. So let's switch this board. I'm used to longer boards or taller boards, so I get kind of crowded in here. Let me try to space things out. Okay, so I'll give you another definition.
I'm not trying to pack several hundred students in here, so.
Okay.
He's like writing big enough for the back of the big room.
That's true, okay, maybe I'll write smaller. So I could take an n-periodic homeomorphism and I can require it to have no periodic curves. So, and then I'm gonna call it atoroidal. Spoiler. If it has no periodic curves. Admits no periodic curves. In the same way that I mentioned earlier with the pseudo-Anosovs up to isotopy. Okay, well then, it shouldn't be surprising. I'll call this a fact, maybe I should call it a theorem. No, I'll call it theorem, they deserve to. I call it theorem. So, theorem. Let's do the field, Tim. Finding, sure, I always get something wrong. Love it, yeah.
So what do you mean by periodic curves?
Yeah, so I mean, I'm thinking of these up to isotopy, so thinking about isotopy classes. And I mean, it's periodic if I take some finite power of the map and I get back to my state. And not zero. This is isotopy. So this is exactly the condition that would give tori in the mapping torus. The picture of the mapping torus somewhere. I see these three curves, they get identified, or just this is under this map, this curve is preserved. See what happens. I mean, this curve is going to this curve. It's when I glue, it's going to be a torus.
Circle cross circle
But
is a
you
torus.
assume that it's n-periodic.
Right, that can also happen with n-periodics.
Yeah.
I could do something silly like do something finite order on this piece. Maybe I'll do something like that. Like because the n-periodic only cares about the ends, I could mess up and do something stupid in the middle of the core of the surface. and get curves that are finite order. Yeah, okay, so that can happen. I can have periodic curves with the end periodic. Okay. So one piece of their theorem, field cam lineage you're loving, is that if F is atoroidal, then the mapping torus is atoroidal. And maybe I'll say the compactification is atoroidal. So now that's a different definition. That's a three manifold definition. Now this means it admits no essential tori. And this is like the major this is the major obstruction that you would have to get a hyperbolic three manifold. Okay. Now I also want to have conditions to make sure that the mapping torus is acylindrical, so no essential annuli. So I'm gonna just say what the theorem is. That is strongly irreducible. Then say MF bar is acylindrical. Let's do that in red. So this means no essential annuli are now like they're properly embedded. So boundary goes to boundary. No essential annuli. So let's just say, for example, this Handel shift homeomorphism, its mapping torus is definitely not acylindrical. There's too many cylinders. Every single curve I draw on the surface is a cylinder. So I need to rule out this behavior, at least first, I need to rule out this behavior where a curve is shifting from this positive end and its orbit suddenly winds up into the negative end. That's like that's one way to get a cylinder. So let's kind of slowly define strongly irreducible. F is strongly irreducible. It's a bunch of no-nos, so no periodic curves. So what I just described just now is called a reducing curve. No reducing curve. Let me also say. Okay. So I'll be more careful. A reducing curve is a curve C, then its box. So that, what do I want to say? I'll say C is both positively and negatively escaping. Under the map F. So it has some, this curve has some power. If I apply some power of F, it's contained inside of one of these escaping neighborhoods. That's what it means to be positively escaping. This curve, if I apply some negative powers of F, now it lives in a negative escaping neighborhood. So I call it negative escaping. But maybe I should say in general, this homeomorphism already gives me a notion of like the positive escaping set and the negative escaping set. Like as a subset of the surface. So if I keep applying, in this case, it's simple because it's the entire surface. The entire surface is both positively and negatively escaping. But in general, if I had like a pseudo-Anosov, I try to, I know that I'm negatively escaping here, and I kind of shift into this core, well, the core is going to tangle things up. And when I shift, I might continue to be tangled. And then I try to shift, but then the map has me stuck. So don't always think that this escaping set is the entire surface. This is just a very simple example. So a reducing curve in this, with this definition, a reducing curve would be a curve C, which is isotopic into U plus intersect U minus. That's another way to actually define this. So that's something I don't want, because that would give me an annulus. And then the last thing I don't want is a periodic arc. No, periodic arc. It's a little bit harder to see. I'll try. So that curve projects to, let's try to doodle one here. And I'll draw it in blue. That curve, let's say on the boundary, for example, projects to some non-separating curve, which intersects this yellow. But then it's on the bottom as well, so I see it here. So now if I look at the flow lines coming out of that arc, I'm sorry, I guess I used the word curve. The flow line coming out of that arc, well, it's just these vertical flow lines that are connecting these. So a periodic arc is also something I don't want. They also give me annuli. So Field, Cam, Leininger, and Loving showed that these are just the three bad things that could happen to give me annuli. And as long as I don't have them, my mapping torus would be acylindrical. Okay. I have no idea what time it is. Oh.
There's some notion of a converse of this theorem?
Yeah, so if F is acylindrical, if MF is acylindrical. If MF is acylindrical, yeah, then there's no way it could have one of these. Yeah, if it has one of these are the most blaring, let's do the converse of if it has one of these conditions, if it's not strongly irreducible, then it has one of these conditions, and those are the conditions that give me annuli. So the converse is like actually a more direct way of saying it. This is the stronger way. Okay, I think I have 5 minutes.
Yeah, about 5 to 10 minutes.
Okay, I haven't defined what I actually do. Let's try to do that.
I was just thinking.
I got distracted, okay. Let's see, so.
Well, we distracted you a bit.
No, I like telling people who haven't seen this stuff because I think it is kind of blowing up now. And I like being, I don't know, I feel like giving talks is like you're a traveling math salesman. People to be more interested in these. Okay, let's see, what can I say in 5 minutes? All right, so let's skip ahead. So these homeomorphisms admit these laminations. Now I'm gonna call them big lambda and big lambda plus, big lambda minus. They're called the Handel-Miller laminations. They're invariant under the map. Maybe talk to me afterwards. I can describe to you like just like pseudo-Anosovs, you can get them from iterating curves. In this case, it's like really nice to see the curves that I iterate are disjoint from each other. So there's just this infinite multi-curve that's living on my surface that converges to a lamination. So I get a positive one from iterating negative curves forward. I get a negative one from iterating positive curves backwards. Okay, so then I can play the same game. If I have a subsurface, it's essential. I should have also said a finite type. I can play the same game that I told you earlier. I can measure, look at the arcs in the curve complex of Y, the arc and curve complex of Y. And then, oh man, I think I just tell you, this is more subtle. If I have a hyperbolic structure, oh man, I think it's just, I got so distracted. Okay, so a toroidal gives me a hyperbolic structure on my manifold. But now, because I have a manifold with boundary, so before I had a closed manifold. So Moss-style rigidity tells me that is a unique hyperbolic structure. It's just one. But now when I have boundary components like that, there's actually a whole deformation space worth of hyperbolic metrics on this thing. And it's like, parameterized by Teichmüller space on each of these boundary components. So if I'm asking about the geometry, I need to like say, okay, what hyperbolic structure? So I'll some space of hyperbolic structures, I'll call it AH of M. And little s is an AH of M. I have to say like, okay, what structure am I talking about? And when it's acylindrical, there is a really nice hyperbolic structure where these boundary components, I'll say S star. There's a unique metric where the boundary of M is totally geodesic. I'll say the unique hyperbolic. So that's why I was building up to like making sure, say, I should add here, when M is acylindrical. So that's like a really nice structure that I want to think about. Okay, so my theorem, I won't quantify it carefully, I'll get time. But essentially, it's the same theorem. Large projection gives me short curves. But now, one version of my theorem tells me that I can find you a structure. There exists some structure so that this is true. Sorry, I wish I had more time to develop
You
this.
can take a moment. You can take a moment to state your theorem.
Okay.
I'm interested in your theorem.
Okay, actually, can I give you a corollary to the finite type world?
Okay.
I think that'll be better. Okay, I think this will be more interesting.
But take a moment. We want to hear about something you did.
Thank you. Okay, I'll give you the better corollary and then come back to this. So this is more understandable. It doesn't even need any types of. This is to me. Okay, so you give me a G. Make it bigger than 2. You give me an epsilon. Then I can find you a closed 3 manifold. I'm going to call it NG epsilon. So it's closed. It's fibered. It's hyperbolic. And it emits. Say it contains a totally geodesic surface. Embedded, I'll say, that's important. Closed subsurface of genus G. And the systole of that, the shortest curve, or what that is, systole, is less than epsilon. So I really like this theorem. Okay, so what am I actually saying? I'm saying I can give you a family of closed fibered hyperbolic manifolds. Each of them, I can find you a totally geodesic subsurface, a closed totally geodesic subsurface of genus G, whatever your favorite G is. And I can also make sure that subsurface has a curve that's like arbitrarily small. So as I move in this family, the curves are getting arbitrarily small. So I don't know, maybe I can yammer, but the point here is that the fiber subsurface does not have this property at all. They are never totally geodesic. They are very distorted inside of the manifold. So it is like really nice that I can find these totally geodesic subsurfaces and I can describe them topologically to you using this infinite type stuff. So let me go back and actually say, that's my theorem C. Let me try to do theorem A. So theorem A, let's quantify carefully. Let's say you give me a D. I'll give you, okay, no, give me a D, and you give me epsilon. And I can find you a K. It depends on D and epsilon. So what is this? So Minsky's theorem depended on the fiber. My theorem depends on a notion of complexity of the map. So I'll say for any F, it's atoroidal and periodic. And then I didn't define this, but this is whatever this notion of complexity is. It's called the capacity genus. I call it the capacity genus. So its capacity genus is bounded by this D. Then for any of those who have bounded complexity, bounded capacity, now I can find you a hyperbolic structure so that for any subsurface, central subsurface, I have this implication. And the K that I use does not depend on the homeomorphism, it only depends on the capacity. So I have Minsky's theorem stated kind of strangely. Okay, and this is what, I need to use this to prove this.
LS, which was, wait, remind me what LS was? Thinking the boundary is less than epsilon. Oh, is that this?
That's the length of the boundary of Y.
The length of the boundary of Y is
But-
less than epsilon, so we
in
have,
this structure.
so if we. Okay, so you're saying that if the distance between these laminations is big enough
Right,
in one of these complexes.
right,
Then the length of the boundary has to be small.
right. In this specific metric,
Okay,
because there's infinitely many, there's a whole continuum of them.
and then you use that to show that you can get all of these. So within a closed fibered
Right.
hyperbolic
Manifold.
manifold, then we have all of these totally geodesic embedded closed surfaces with very small curves.
Very short curves, yes.
So
just to
the
walk.
manifold depends on the epsilon.
Right, the manifold depends on the G and the epsilon, so it's changing as G and epsilon change.
Okay.
So I'm not saying I fix it and I get a lot of them.
What does fiber mean?
Oh, fiber means it's a mapping torus in the finite type world. So picture's gone, but
Yeah. And then you glue by the knot.
Yeah, no, it's a suspension flow, I can understand.
yes.
These are dynamics.
Yeah, I figured.